Okay, picture this. Imagine our entire solar system isn't just floating in, empty space,
Hmm.
but it's actually cocooned inside this gigantic, invisible bubble.
Right.
Think of it like our own personal cosmic force field,
Yeah.
kind of deflecting all sorts of dangerous particles zapping through the galaxy.
Yeah, that's a good way to put it.
Now, this bubble, it isn't static, is it? It's constantly interacting with the space outside.
Exactly, like a ship moving through cosmic currents.
And how that boundary behaves way out past the planets
Yeah.
turns out to have, well, surprising effects right here on Earth.
It really does.
That bubble, that's the heliosphere. And this deep dive is all about exploring it.
Mm-hmm.
We're going to figure out what it is, what exactly it shields us from these high-energy things called cosmic rays,
Right.
and uncover the complex dynamic interactions happening at the very edge of our solar system, where the sun's influence finally meets the wider galaxy.
Yeah, that fascinating boundary region.
We've pulled together a really interesting stack of material for this. We've got sources digging into cosmic rays, breaking down the heliosphere structure,
Its boundaries.
its boundaries, analyzing its interactions with interstellar space, and even looking at the ripple effects these things can have back here on Earth and, on our technology.
A lot to unpack there.
So our mission today is to unpack all of this, to really understand this incredible shield, what it protects us from, and what happens when our solar system's bubble kind of bumps up against the rest of the universe. Let's dive in.
Okay. Well, what's truly remarkable is that this huge bubble, it extends billions of miles.
Billions.
It's actually created and maintained by something starting right at the sun. The heliosphere is essentially this vast region dominated by the solar wind.
The solar wind, right. That stream of particle.
Exactly. A continuous torrent of charged particles, mostly protons, electrons streaming out from the sun's outer atmosphere at supersonic speeds.
Supersonic, wow.
And this isn't just some gentle breeze. It's a really powerful outflow. It pushes outwards, and it carries the sun's magnetic field with it.
Ah, the interplanetary magnetic field.
That's the one. And this outward push is what inflates the heliosphere, forming that protective bubble we talked about.
Okay.
Its main job, like you said, is acting as a shield. It deflects a huge amount of harmful radiation coming from outside our solar system.
Okay, so the sun's constantly inflating this bubble with its wind and magnetic field.
Yeah.
But what's the big threat it's shielding us from? You mentioned cosmic rays.
Exactly. Galactic cosmic rays, mostly. These are fundamentally different from particles coming off the sun itself, like in solar flares.
Right. Different source entirely.
Totally different. Galactic cosmic rays are incredibly high-energy particles. We're talking mostly atomic nuclei stripped bare, accelerated almost to the speed of light by, well, cataclysmic events out in the galaxy.
Like what kind of events?
Things like supernova explosions, the messy aftermath of black holes, other really powerful astrophysical processes.
Yeah.
Stuff that packs a huge punch.
And the challenge is just their sheer energy.
It's their energy, yeah. They're so energetic they can blast right through things. If the heliosphere didn't exist, the amount hitting the inner solar system, hitting Earth,
Would be much higher.
much, much higher. And potentially far more damaging to life and technology.
So we've got the sun's bubble pushing back against these incoming cosmic rays, but the sources show it's not just one simple wall, right? It's got layers, like a cosmic onion.
Yeah, a cosmic onion. I like that. As the supersonic solar wind rushes out, it eventually slams into the stuff between the stars, the interstellar medium, or ISM.
Gas and dust.
Mostly gas and dust, yeah. And this collision creates a series of distinct boundaries, these layers.
Yeah, what's the first one?
The first major one is the termination shock. This is where that supersonic solar wind, after traveling billions of miles unimpeded, suddenly hits the brakes.
Hits the brakes.
It slams into the resistance from the interstellar medium and abruptly slows down to subsonic speeds. It's a shock wave, basically.
By subsonic, then what?
Beyond the termination shock, you enter this turbulent region called the heliosheath. Here, the solar wind isn't supersonic anymore.
Right.
It's been slowed down, it gets heated up, and it's compressed by the pressure from the interstellar medium pushing back. It's a very messy, energetic zone.
And the final layer, the edge.
That's the heliopause. This is the true outer edge of the heliosphere. It's the point where the outward pressure from our solar wind finally balances the inward pressure from the interstellar medium.
So the sun's influence basically stops there. Magnetic fields, particles.
Pretty much, yeah. That's the boundary of the sun's dominant magnetic and particle influence.
Now, I've heard about something called a bow shock. Is that part of this structure, like a Wave in front.
Ah, good question. Theoretically, yes. If our heliosphere were moving supersonically through the interstellar medium, you'd expect a strong bow shock out front, like the wave made by a boat.
Makes sense.
But what's really interesting and still kind of debated is that recent data, especially from the Voyager probe.
Little explorers out there.
Exactly. Their data suggests that if a bow shock exists for our heliosphere, it's actually much weaker than models predicted, or maybe even non-existent.
Huh. Why would that be?
It tells us something specific about the interstellar medium we're currently moving through. Maybe it's denser or slower relative to us than we thought, or the magnetic field out there plays a bigger role. It's an active area of research.
So it's layered, but maybe not a perfect sphere either. I remember reading it's more squashed.
Exactly right. We used to think maybe spherical, but now we understand it's asymmetrical, probably shaped more like a comet.
A comet? Seriously?
Yeah. It seems to have a sort of rounded nose pointing in the direction the sun is traveling through the galaxy,
Okay.
and then a very long tail stretching out behind it. We call it the heliotail. And even that tail seems complex, maybe layered, changing with the sun's magnetic cycle.
Wow. Okay, this boundary, the heliopause, where our bubble meets interstellar space. What's actually out there? What's this interstellar medium made of?
Right, so it's not empty. It's sparse, for sure, but it contains gas, mostly neutral hydrogen atoms, actually.
It's floating hydrogen.
Yep, plus some charged particles, ions, and crucially, its own magnetic field permeating the galactic magnetic field, or GMF.
And that's what's pushing back.
That's the stuff pushing back against the solar wind at the heliopause. That boundary is incredibly dynamic.
How so?
Well, this is where the sun's magnetic field, the HMF carried out by the solar wind, directly meets that galactic magnetic field, the GMF.
Okay, two magnetic fields colliding.
Exactly. And they interact, they can tangle, reconnect, snap, create turbulent magnetic regions. And that turbulence, it hugely affects how easily particles, including those cosmic rays, can get into or out of our solar system.
And we know this for sure. How?
We have direct witnesses.
Yeah.
The Voyager 1 and Voyager 2 spacecraft, incredible missions.
Still going after all this time.
Launched in the 70s, they actually crossed the heliopause, Voyager 1 in 2012, Voyager 2 in 2018.
Wow. And what did they find?
They saw exactly what theory predicted. A sudden, sharp drop in particles originating from our sun, and at the same time, a big increase in the galactic cosmic rays coming from outside.
Telltale sign.
The smoking gun. They had punched through the bubble and entered interstellar space proper.
That's just amazing. But is it like a solid wall they pass through?
Not quite. It's more permeable, you could say. For instance, those neutral hydrogen atoms from the interstellar medium.
The ones that are just floating out there?
Yeah, because they're electrically neutral, they aren't really affected by the magnetic fields at the boundary. They can just drift right across the heliopause into our solar system.
Oh, interesting. So stuff from outside gets in.
Some stuff does, and once those neutral atoms are inside, they can get zapped by sunlight or collide with solar wind particles and lose an electron. They become ionized.
Okay.
Then they're called pickup ions. Now they are affected by the magnetic field, and they get swept up by the solar wind, actually changing its flow and properties slightly from the inside out.
So wait, does that mean we can actually see or sense this distant boundary from inside the heliosphere using those incoming particles?
Yes, exactly. That's a key technique. When a fast-moving solar wind ion hits one of those incoming neutral atoms, they can swap an electron, charge exchange.
Right.
The solar wind particle becomes neutral, and suddenly it's free. It's not tied to magnetic field lines anymore, so it travels in a straight line. These are called energetic neutral atoms, or ENAs.
And we can detect those.
We can. Because they travel in straight lines, our instruments can trace their paths back to where they were created, near the heliosphere's boundary. Missions like IBEX, the Interstellar Boundary Explorer,
I've heard of IBEX.
and the upcoming IMAP mission, launching around 2025, they're designed specifically to detect these ENAs. By mapping where ENAs come from, we can build up a picture of the heliosphere's shape and the conditions at the edge, all from our vantage point deep inside.
That's clever. Mapping the invisible bubble from within. Okay, so the heliosphere is our layered, comet-shaped shield, constantly interacting with the outside. How good a job does it actually do at stopping those cosmic rays?
Well, it acts as a cosmic ray modulator, is the term often used. It doesn't block all of them, nothing's perfect,
Right.
but it significantly reduces the number that make it into the inner solar system. And here's where it gets really interesting. The level of shielding isn't constant.
Ah, Because the sun changes.
Precisely. It's intimately tied to the sun's 11-year activity cycle.
Okay, explain that.
Think of the heliosphere's shielding power like a cosmic dimmer switch controlled by the sun. During solar minimum, when the sun is relatively quiet, fewer sunspots, fewer flares,
Mm-hmm.
the solar wind tends to be smoother, less turbulent, and its magnetic field is a bit weaker or simpler in structure. This means the heliosphere offers less resistance to incoming galactic cosmic rays.
So more get through.
More get through. They can penetrate deeper into the solar system, reaching Earth in greater numbers.
Okay, and the opposite, solar maximal.
Right. During solar maximum, the sun is much more active, the solar wind is stronger, gustier, more turbulent, and the interplanetary magnetic field is more tangled and complex.
A stronger defense.
A much better shield, exactly. It deflects more cosmic rays, scattering them away, reducing their flux in the inner solar system. It's kind of wild to think sunspots on the sun affect how much high-energy radiation hits us from across the galaxy.
Wow, so the sun's mood really does change how protected we are. But even with the shield, you said some cosmic rays still make it through. What actually happens when those incredibly energetic particles hit Earth?
Yeah, this is where that distant boundary starts to have tangible effects right here at home. When those GCRs reach our upper atmosphere, they collide violently with air molecules, nitrogen, oxygen.
What happens in the collision?
They cause atmospheric ionization. Basically, they knock electrons off the air molecules, creating ions and triggering showers of secondary particles.
Okay, and that ionization matters because...
Well, it can kickstart chemical reactions. For example, in the stratosphere, it can increase the production of compounds like NOx, nitrogen oxides, and hydrox hydrogen oxides.
And those are bad for ozone.
They are known ozone-depleting substances, yes. So the thinking is, a significantly higher flux of cosmic rays could potentially lead to some level of ozone depletion over time.
Which means more UV radiation reaching the surface.
Potentially, yes. That's one possible effect.
What else? I remember reading something about clouds.
Ah, yes, that's a fascinating and still somewhat debated hypothesis. The idea is that the ions created by cosmic rays might act as tiny seeds or cloud condensation nuclei.
Seeds for clouds.
Yeah, points where water vapor can more easily condense to form cloud droplets. So the hypothesis goes, if you have more cosmic rays, you get more ionization, maybe you get more cloud seeds.
And potentially more clouds.
Potentially more clouds, particularly low-altitude clouds, which tend to reflect sunlight back into space and have a cooling effect on the climate.
So hang on, are you saying cosmic rays could actually influence climate? That sounds like a huge deal.
It would be a huge deal, which is why it's such an active area of research, and also why that specific link, cosmic rays, cloud formation, climate, is still debated in the scientific community.
So no consensus there.
No consensus on it being a major driver for, say, recent climate change. But some theories suggest that over much longer geological timescales, big shifts in cosmic ray flux could play a role in modulating Earth's overall energy balance.
Like ice ages, maybe.
There are hypotheses linking extreme cosmic ray events, maybe from nearby supernovae or changes in the heliosphere, to past climate shifts like ice ages. But again, those connections are still being explored and aren't, widely accepted as the primary cause. It's complex.
Okay, beyond the atmosphere and climate stuff, what about more direct impacts? On life, on our technology.
Right. On a biological level, these high-energy particles can penetrate tissues, they can damage DNA, cause mutations.
So evolution, cancer.
Over vast evolutionary timescales, yeah, this background radiation probably contributes to the mutation rate. For individuals today, the risk is generally very low at sea level because the atmosphere provides good shielding.
But higher up.
Higher up, yes. Airline crews get slightly higher doses. And for astronauts in space, outside most of the atmospheric and magnetic shielding, it's a major concern. Managing cosmic ray exposure and the increased cancer risk is a huge challenge for long-duration spaceflight.
And our tech. Satellites and
Well,
things.
yeah. Technology is quite vulnerable. Cosmic rays can cause what are called single-event upsets or bit flips in microelectronics.
It flips.
Like,
In computers.
exactly.
Yeah.
Flipping a binary 0 to a 1 or vice versa. This can cause temporary glitches, data corruption, even permanent damage in sensitive chips. It's a big issue for satellites, obviously, and even for avionics and high-flying aircraft.
And communications, too.
Intense bursts of particles, sometimes from the sun but modulated by the heliosphere, can definitely disrupt radio communications, especially high-frequency radio.
Wow. And you mentioned we have evidence from the past. like in tree rings.
Yeah, that's really cool. When cosmic rays hit the atmosphere, besides ionization, they also create rare isotopes, cosmogenic isotopes like carbon-14 and beryllium-10.
Okay.
These isotopes get mixed into the atmosphere, absorbed by plants, trapped in ice layers as snowfalls. So by analyzing things like tree rings for carbon-14 and ice cores for beryllium-10,
You can see how much was around back then.
exactly, scientists can find spikes in these isotopes, which tell us there were periods in the past with unusually high cosmic ray flux hitting Earth.
And what do those spikes correlate with?
Often they correlate with periods of known weak solar activity like the Maunder minimum or potentially even bigger events like nearby supernova explosions. It's like reading a history book of our cosmic ray environment written in trees and ice.
That's incredible. A cosmic history lesson.
Okay.
Okay, so we know the shield changes based on the sun's 11-year cycle. But the sources also point out something bigger picture. Our whole solar system is moving.
That's right, a critical point. We're not sitting still in the galaxy.
Where are we going?
We're orbiting the center of the Milky Way, and as we do, we pass through different clouds of gas and dust, different regions of the interstellar medium.
So the outside environment changes.
Precisely. Right now, we seem to be in a relatively warm, low-density patch called the Local Interstellar Cloud, or LIC, but over thousands, tens of thousands of years, we'll inevitably move out of this cloud and into others with different properties.
And how does encountering a new interstellar region change our heliosphere, our bubble?
It can change it significantly. The properties of that external environment, the stuff pressing in from the outside, can alter the heliosphere's size, its shape, and crucially, how well it shields us.
Okay, give me an example. What if we enter a denser cloud?
Right. If the solar system moves into an interstellar region that's significantly denser, more atoms per cubic centimeter out there.
More stuff pushing back.
Exactly. It exerts more external pressure on the heliosphere. It would act like squeezing the bubble.
So it shrinks.
It would likely compress the heliosphere, shrink it, bringing those boundaries like the termination shock and heliopause closer to the sun. And generally, a smaller heliosphere means a weaker shield.
Allowing more cosmic rays in.
Potentially, yes. More GCRs could reach the inner solar system.
What about the magnetic field out there, the GMF?
Also crucial, if we pass into a region with a much stronger galactic magnetic field, that external field can exert more influence. It could distort the heliosphere's shape more dramatically.
Making it less like a comet, maybe?
Maybe flatter or stretched in different ways. It could also increase the magnetic turbulence at the boundary region, the heliopause.
And more turbulence means?
Often means more potential pathways for cosmic rays to sneak in. It complicates the interaction.
Okay, what else? Speed. Does how fast we move matter?
The relative speed between the sun and the interstellar gas matters too. If we were to enter a region where our motion relative to the gas was significantly faster, or if the gas itself was moving towards us rapidly.
But hitting a headwind.
Sort of. It could potentially reignite the debate about the bow shock, maybe creating a stronger one out front, heating and compressing the interstellar gas before it even reaches the heliopause.
Changing the initial conditions of the interaction.
Right. And one more thing. The ionization level of the interstellar medium, remember those neutral atoms that drift in?
Yeah, the hydrogen.
If we enter a region that's much richer in neutral atoms compared to ions, more of them could penetrate deep into the heliosphere. They get ionized inside, become pickup ions, and that can alter the solar wind dynamics and the boundary structure from within.
So many ways the outside environment can reshape our shield. Taking a step back then, what does this possibility our heliosphere changing as the sun journeys through the galaxy? What does that mean for you, the listener? What are the real implications for Earth?
Well, it reinforces this key idea. Our cosmic shield isn't permanent or unchanging. If our solar system passes through, say, a denser or more strongly magnetized interstellar cloud in the future,
Which seems likely over long timescales.
it seems inevitable, yes. Then our heliosphere could shrink or become more porous to cosmic rays. This would lead to increased cosmic ray exposure right here on Earth.
And we talked about what that could mean.
Exactly. Higher cosmic ray levels have those potential, though still debated, influences on things like cloud formation and maybe climate over long periods. They definitely contribute to the background rate of biological mutations.
And the risks for technology and astronauts go up.
Significantly. Higher radiation poses greater risks for satellites, for aviation electronics, navigation systems, and critically for human space exploration trips to the moon, Mars, wherever we go beyond Earth's protective magnetic field. Astronaut safety becomes even more challenging.
Could it affect space weather too? Like solar
That's
storms?
another possibility. A compressed or significantly disturbed heliosphere might alter how solar storms, CMEs, propagate through space. Perhaps their effects could be felt more intensely closer to Earth under those conditions.
So understanding this really distant boundary isn't just, abstract astrophysics.
Not at all. It's directly relevant to practical things like space weather forecasting, protecting billions of dollars worth of technology, ensuring astronaut safety, and even helping us understand planetary habitability in general. How important is a strong heliosphere-like shield for life to thrive elsewhere?
Which makes missions like IBX and especially the upcoming IMAP so vital then for mapping this and understanding how it reacts.
Absolute and crucial. IBX gave us those first amazing maps using the ENAs. IMAP is designed to provide a much more detailed, higher resolution 3D picture of the boundary.
What else will IMAP do?
It aims to really dig into the physics out there, how particles get accelerated at the termination shock, how the solar wind interacts with the interstellar medium, how the heliosphere filters those cosmic rays. Combining that kind of direct measurement with astronomical observations mapping the nearby interstellar clouds.
Helps us predict the future environment.
It helps us understand how our cosmic shield has behaved in the past, how it's reacting now, and gives us a better chance of predicting how it might evolve as the sun continues its long journey through the galaxy.
Okay, so wrapping up this deep dive then, we've explored the heliosphere as our solar system's protective bubble,
Our cosmic shield, yeah.
learned about the high-energy cosmic rays it defends us against, delved into the really fascinating dynamic boundary layers where our solar system meets the wider galaxy,
The termination shock, heliosheath, heliopause.
and seen how changes in that external interstellar environment, the stuff we're flying through, can directly influence the shield with potential knock-on effects right back here on Earth.
It really underscores how interconnected everything is, doesn't it? Even across these vast cosmic distances.
It truly does. And thinking about that long journey the sun is on, moving through different interstellar neighborhoods over tens, hundreds of thousands of years,
Mhm.
it does leave you with a final thought, doesn't it?
Mm.
What might the heliosphere and our level of protection from cosmic rays actually look like far, far into the future? How will our cosmic shield evolve as our solar system sails through new galactic waters? And what could that mean for the long-term environment? Maybe even the slow march of evolution here on Earth.
It's a mind-boggling prospect to consider, looking that far ahead into our cosmic future.